Hello all, in this lesson we're going to be studying the nucleus. Here's our bookwork, keeping it short, and our aim. What is the nucleus of an atom, and how is it described? Please copy down these particular do now questions without answering them, and we'll work on those in class. So the strong nuclear force is, as I'm sure you're guessing, a very strong force in the nucleus of an atom. And there are other forces in the atom that we already know about. For instance, we do know that two protons, both of which are positive, would repel each other. But if that were the only force, then very quickly the atom's nucleus would fall apart. And that's because these two protons, both of which are positive, would repel each other, and then they would explode the nucleus, and the neutrons would leave as well. So there must be another force inside the nucleus that holds it all together, and that's called the strong nuclear force. The strong nuclear force exists between protons and neutrons, and it's a very strong force, the very strongest one we know about. However, it only works in this very small area of the nucleus. So that's something to keep in our back pocket, that it only works in such a small distance. And just know that the force that holds it all together is called the strong nuclear force. Okay, so the universal mass unit. So in short, the universal mass unit is just the weight of a proton or a neutron. They're both about one universal mass unit. And how many protons, neutrons, and electrons does a carbon-12 atom have? So based on this 12 right here, I can tell that it has a mix of protons and neutrons in probably equal ratios. So let's say that it has 6 protons and 6 neutrons. Now the reason for that, again, is that the 12 is saying how heavy it is, so it must be 6 and 6. It also has 6 electrons, although electrons have no mass, or very little mass. All right, so here are some more precise numbers. So in universal mass units, the mass of the proton is this many, the neutron is just a little bit more, and the electron is super small. In SI units, which would be like kilograms, then we can see that we have this many kilograms per universal mass unit, so a very small number. What is the mass of a hydrogen nucleus that contains no neutrons? All right, so a hydrogen nucleus with no neutrons is simply a single proton. So I think the best answer for this one is just to say one universal mass unit. But this next one's a little bit harder. What's the mass of a helium-4 nucleus containing 2 protons and 2 neutrons? So let's say that it's in universal mass units. Then it's going to be 1.0073 per proton, but there are 2 protons in a helium-4 nucleus. There are also 2 neutrons. I'll go ahead and label these. These are the 2 protons. Here are the 2 neutrons. And the neutrons are 1.0087, and that's also going to be times 2. And after that multiplication and addition, I got 4.032. All right, so the mass-energy relationship was really very well described by Einstein when he used the equation E equals mc squared. It basically just says that the energy in a certain amount of mass is when you multiply the mass by the speed of light squared. So we know the speed of light, it's 3 by 10 to the 8th, but the speed of light squared is going to be 9 by 10 to the 16th. The mass will always be in kilograms, and the energy will come out in joules. Let's do an example. Let's calculate the amount of energy in joules that would be produced if 2.5 by 10 to the negative 3rd kilograms of matter was entirely converted into energy. So E equals mc squared. That's the mass we're dealing with, and here is the speed of light squared. When I just do the multipliers to start, I'm getting 22.5 times 10 to the something, and this is going to be to the 13th power. And in proper scientific notation, it's going to be 2.25 by 10 to the 14th joules. Here's another sample problem. 1 universal mass unit equals 1.66 by 10 to the negative 27 kilograms. Calculate the energy in mega electron volts. So we'll start with E equals mc squared and plug in the mass that we know and the speed of light squared. So I did that, and now it's time to solve. And with just the multipliers, I got 14.94 times 10 to the something. And that's going to be negative 11 joules. But I need to convert this into electron volts and then into mega electron volts. So I'll start back fresh over here. 14.94 by 10 to the negative 11. And yeah, I know this isn't in scientific notation yet, but we're not even done, so it's all right. So in this conversion, I'm going to use a joules to electron volts conversion. And I found on the first page of the reference table that 1 electron volt is equal in size to 1.6 by 10 to the negative 19 joules. So we just need to multiply through on the multipliers first. And I got 9.34 by 10 to the 8. The joules cancel, so this is going to be in electron volts. So let's do one final step where we convert to mega electron volts. So 9.34 by 10 to the 8 electron volts. And we want electron volts on the bottom and mega electron volts on the top. And each mega electron volt has 10 to the 6 electron volts in it. So our new answer is going to be 9.34 by 10 to the 2 mega electron volts after the electron volts cancel. So that's my answer. So I sort of just did it the math way just to prove that it could be done, but there is a nice little thing on your reference table that says a universal mass unit is equal to that many mega electron volts, and you can see the similarity between those two. There was just a little bit of error because of rounding, but they did ask me for a universal mass unit in mega electron volts, so I probably should have just solved it this way. But you know me, sometimes I do it the hard way. So one of the things that you'll hear a lot from science teachers and regular folks a lot is the law of conservation, which says that matter cannot be created or destroyed. But this is not exactly true via the equation E equals mc squared. Because this equation tells us that energy can, in fact, be converted into matter, and vice versa. However, matter isn't really being created or destroyed as much as it's being rearranged or formed into a new product. Meaning, as you convert energy into mass or mass into energy, it's just a new form. So that's the main gist of this slide, but basically it's also saying that the tiny amounts of mass that are lost in an atom when it reacts and produces energy are too small to be measured. So earlier we had said that the mass of a helium-4 nucleus would be about 4.0320 universal mass units. The way we did that was we just took the mass of a proton, multiplied it by 2, and added the mass of a neutron, which was multiplied by 2, and we got that. However, when you actually are able to measure the mass of a helium-4 nucleus, you'll notice that it is slightly less than the projection. The reason for that is when any of those subatomic particles, the protons and the neutrons, and when they come together and they bond to each other to form that element, they are going to release a certain amount of energy in the process. It's part of the bonding process when energy is released. But that also means that the energy is coming from the loss of matter. So it's really the difference between this number and this number which will produce the energy from that reaction. So let's put this into practice. A deuterium nucleus has a mass of 1.53 by 10 to the negative 3 universal mass units, less than, I will highlight that, less than its components. So that means that there was a tiny amount of mass that was sort of unaccounted for, rather than just sort of adding up to its components. So what we're going to do is we're going to take this amount of mass and we're going to assume this is the mass that was converted into energy. And I just found this entry on the front page of the reference table that relates each universal mass unit to a number of mega electron volts. So I'm just going to take my initial data of this universal mass unit and convert it to this number of mega electron volts. So there's our original amount, and I need to have universal mass units on the bottom and mega electron volts on the top. And apparently 931 mega electron volts is equal to 1 universal mass unit. And I'm getting 1.42 mega electron volts as my answer. Let's do the sample problem together. A helium nucleus consisting of 2 protons and 2 neutrons has a mass of 4.0016. I'll highlight that, that's going to be important. But the mass of a proton is this and the mass of a neutron is this. First, let's find the difference between the mass of the helium nucleus and the total mass of its constituents. So we'll start by finding the mass of the protons. It's going to be found that way, multiplying the mass of 1 proton times 2, and we'll have to add that to the mass of a neutron times 2. And as we've shown before, this comes out to be 4.032 universal mass units. Now let's subtract from that the stated actual mass of 4.0016. And I got a difference of 0.0016 universal mass units. Now in the second step, we need to convert this amount of mass into energy, specifically in electron volts. So this is essentially a conversion. We'll keep universal mass units on the bottom and electron volts on the top. I'm going to have to use mega electron volts because of this relationship. And it's going to say 1 universal mass unit is 931 mega electron volts. So we basically just need to do the 931 and multiply it by 0.0016. And I'm getting 1.4896, which we can really probably just say 1.49. And this is going to be mega electron volts, but they asked for the answer in electron volts. So there's one more conversion, and that would be back into electron volts. So each mega electron volt is going to carry 10 to the 6 electron volts. So that means our final answer is going to be 1.49 times 10 to the 6 electron volts, because these mega electron volts cancel. And lastly on this slide, I just wanted to point out that we use these things called particle accelerators to study these nuclei. Particle accelerators are essentially giant magnets, and they are able to push around charged particles like protons, electrons, and other things. They actually are useless on things like neutrons, and that's because magnetic fields only affect charged particles and neutrons don't have a charge. But these magnets are so strong that they can make these particles move at speeds close to the speed of light, and then they just slam them into other particles and see what kinds of broken bits come out. And by studying all these broken bits, we get this really amazing insight into the inside of a nucleus. Expect that you will see lots of news clippings and all kinds of new research coming out of these particle accelerators, because this is really the direction that physics is going now, is what's going on inside the atom. And with that, we have reached our pair up. Of course, I will make copies of these glorious questions for you. And these summary questions I need you to copy down because we're going to do them in class next time I see you. Thank you for watching.